Next thing we want to talk about is conductivity. So conductivity. We've seen that little I, or electron current, is equal to NAV, where V is the drift speed. V is equal to mobility times electric field. So little I is NAUE. Capital I is then the charge of an electron, or the charge of whatever the mobile charge is in the conductor, times NAUE. So when we're thinking about how easy is it for a current to flow given a particular electric field inside a conductor, it depends on a number of things. It depends on the mobility, depends on the cross-sectional area of the wire, depends on the electron density. Okay, so let's just write these things again. Just a reminder, this is mobility. N is the electron density. It depends on the charge, too. I mean, the charge of an electron isn't going to change, of course. But you can think of other types of conductors, like maybe aqueous solutions, where the mobile charges might not be electrons. They might be doubly charged ions or something like that, right? So the charge would make a difference as well. Well, all of those quantities, Q, N, and U, are properties of the material. Okay, the area is the property of the geometry, right? That depends on how big you make the wire. But Q, N, and U are all properties of the material, and they all affect how easy it is to get a current to flow given a certain electric field. Individually, they're tricky to measure. We can't actually do it, and we'll see later when we get to magnetic forces a way to measure some of these quantities. Individually, they're tricky to measure, but grouped as a whole, we can measure it more easily. And so we're going to define something. This is a Greek letter lowercase sigma. Looks like a O with a little curl on it. That quantity, Q times N times U, is called the conductivity. And it's just a measure of, again, how conductive a conductor is, meaning how easily can the charges flow given a particular electric field applied to it. Okay, so sometimes this is rewritten I over A. This is current per unit cross-sectional area. Sometimes this is called the current density. We're not going to talk too much about this, but you might see it in future courses, so just giving you a little heads up. This is sometimes given the symbol capital J. Okay, it's just the number of amps per meter squared. Okay, so capital J is equal to sigma times E is another way of stating this relationship. And this is something you may see in if you take an electrical engineering or intermediate electromagnetism class. But it's nothing more than just restating I equals NAUE. Okay? So let's just try a quick calculation. Again, nothing too fancy here. If you know that copper has a electron density of 8 times 10 to the 28 electrons per meter cubed, and a mobility of 4.5 times 10 to the minus 3 meters per second divided by newtons per coulomb, what's the conductivity? And the units are kind of funny looking, but we'll simplify the units in just a second. Per meter squared divided by volts per meter. So it's going to be ampere meter squared volts. And then so it's going to be that. It's actually going to be ampere divided by volt meter. Okay. And in just a second, we'll introduce the ohm. And so, in fact, conductivity is really measured in per ohm meter. Okay. So it's a little funny looking for right now, but we'll simplify it in just a second. Okay. Answer number 3, 5.76 times 10 to the 7. What's the charge we're multiplying by? Yeah, the charge of an electron, right? Because we know that the mobile charges in copper are electrons. So it's 1.6 times 10 to the minus 19 times, what do we say? The N is 8 times 10 to the 28th. And the mobility is 4.5 times 10 to the minus 3. Or, yeah, 10 to the minus 3. And so that should give you 5.76 times 10 to the 7. So the units, we have coulombs, we have electrons per meter cubed, and we have meters per second divided by volts per meter. So it looks kind of ugly. We have meters squared here, and meter squared is going to cancel out with that and leave a meter here. And a coulomb per second is an amp, and so we have amps divided by volt meters, so which is the same thing as that, only unsimplified. Okay, so that's conductivity of copper. 10 to the 7th in these units is typical conductivity for a high conductivity for a metal, copper, gold, silver, that sort of thing. Carbon, on the other hand, conductivity of carbon, which is not a good conductor, often considered just an insulator, is about something like 10 to the 4th, okay, 3 times 10 to the 4th. So just to give an example of how big these quantities can be. One other thing you might run into is a quantity called resistivity, which is just 1 over the conductivity. And it's given the symbol Greek letter rho. It's equal to 1 over sigma. Okay, so sometimes it's easier to measure how much the material resists the flow of electricity than how much it conducts electricity. So that may be something, again, you might run into. We're not going to talk too much about it. Okay. Now I told you that, so I can introduce another quantity called resistance. Okay, so we've got current per unit area is equal to conductivity times electric field. Okay, so let's look at a wire, for example. So this is a segment of a wire that's connected to a longer circuit. Okay, it has a cross-sectional area A. It has a length L. And inside the wire, there's an electric field in some direction. And it's going to cause a current to flow. Conventional current would flow in the same direction. The electric field can be calculated, but directly it's often tricky to measure. Okay, it is easier to measure potential differences, and you've done this in lab. You've gotten a voltmeter out, connected your voltmeter to two ends of a wire, and you get a reading. So you get a voltage. Okay, and the voltage in here, the magnitude of the potential difference across the wire, is going to be the electric field times the length. So I can say that the electric field is the potential difference over L. Let me plug that back into here. So I have I over A is equal to sigma times delta V over L. Current, I can also measure the current by, again, pretty easily by just putting an ammeter in the circuit, get a reading there. So let me isolate current on one side, and we have sigma times A over L times delta V. So this is saying that the amount of current I'm going to get is going to be proportional to the potential difference across that wire. And this quantity consists of two things. It consists of material properties, namely a material property, namely the conductivity, okay, Q times N times U. Q, N, and U are going to be the same no matter how much of the material you have, okay? So that's on a per volume basis, okay? But then we have the geometry of the actual wire, okay, how wide it is and how long it is. So all those quantities are combined into something we're going to call resistance. I'm going to say that resistance give it the symbol capital R, is equal to the length divided by sigma times A, okay? So in other words, if I make the wire longer, I'm going to get less current, given the same potential difference. If I make the wire thicker, if I have a fatter wire, I'm going to get more current, given the same potential difference. If I have the same shape of an object, but just something with a higher conductivity, I get more current, okay? So we're going to put this in terms of resistance, where it's going to be 1 over this, and say that, erase some of this, that conventional current then is going to be delta V over R. So in other words, if any of these things changes, if the wire gets longer, if the conductivity increases, if the conductivity decreases, or if the area decreases, the resistance goes up. So we have a bigger resistance to the flow of current, right? And again, this is one of these things where it's easier to measure. You can just, if you know the potential difference and you know the current, you can just easily measure this quantity with a couple of meters, okay? Anybody seen this formula before? Yeah, or you may have seen it as delta V is equal to I times R. This is sometimes called what? Ohm's law, which isn't a particularly great name because it's not really a universal law. It's just describing how current is related to potential difference in conductors, in particular types of materials. Okay. Okay. So resistance. It's measured in units of ohms. So the symbol, the unit of measurement is called an ohm, and the symbol is capital omega, Greek letter omega, hence ohm. Okay. Which also means we could write conductivity, by the way, since conductivity has units of amps per volts over meter. Notice that 1 ohm, I write this, IR is equal to delta V over I. That's a volt per amp in units. That's 1 ohm. So 1 ohm is equal to 1 volt divided by 1 amp here. Which means conductivity can be written in units of 1 over ohms times meters. Okay, so you may see that unit as well. Conductivity. Okay, that's resistance. Let's try a quick calculation here. Okay, a long light bulb is connected to two 1.5 volt batteries, and we measure the current to be 0.075 amps. What's the resistance of the long bulb? It should be pretty straightforward. All right, clearly it's got to be 40 ohms. Is that right? Oh, yeah, because it's two batteries. That's right. So the total potential difference is 3 volts. That's right. So 3 volts divided by 0.075 amps is going to give you 40 ohms. Okay, so that's resistance. All right. Now, it's nice, and we often like it when we have a resistor, an object, an element in a circuit that has a constant resistance, meaning no matter what potential difference we apply across, we get a current that's obeying this proportionality. And so if we have what's called an ohmic resistor, or an ohmic element, ohmic behavior, we're plotting the current as a function of the potential difference across the resistor. Okay, you can imagine having sort of a variable power supply or a variable battery, and you're cranking the potential difference up. And if the resistance is constant, then the graph should look like what? Should look like a straight line, right? Should look like a straight line where at 0, delta V equals 0, the current is 0, and just goes up as you get a larger potential difference. And the slope of this is what? Not R. If I is equal to delta V times, should be 1 over R, right? 1 over R. So the slope here is 1 over R. Okay, so that's an ohmic resistor. But it's very important to know that not everything is ohmic, okay? And in fact, for most materials, what you would find is that there's going to be some limit to this behavior. If you start cranking up the potential difference too large, provided you don't blow a fuse or anything like that first, you would see something like that, where the slope gets smaller and smaller. So the slope is decreasing, and therefore R must be increasing with a higher potential difference. What do you suppose would make the resistance go up when you start getting larger and larger potential differences and therefore larger and larger currents flowing across, say, a light bulb or other sort of element? Say again? Heat. Okay, so the temperature is going up, right? Temperature is going up. R is equal to L over sigma times A, and we said that the conductivity was Q times N times U times A. You raise the temperature, what's going to change? Well, it may actually expand if you're talking about, say, a filament in a light bulb, if you raise the temperature, it may actually expand a little bit, so the length might change, but not very much. The area is probably not going to change very much. Is the charge actually going to change? The mobile charges? No, that's not going to change. Is the number of available electrons per unit volume going to change? Well, that's a good question. We think that's basically due to quantum mechanical properties, right? We know that metals are giving up 1 electron per, most transition metals, I should say. It may vary, but on average, it's giving up 1 or 2 electrons per atom to the mobile electron C. In semiconductors, that might actually change. The number of available electrons might actually change in a semiconductor. But in metals, typically that stays constant. It's the mobility that's going to make a difference. The mobility is going to make a difference because what's in our model of conductors, what's happening? What's impeding the flow of electrons? Yeah, nuclei, and they are, so electrons come along and collide with, and it's not just the nuclei, but it's sort of the inner core, the nucleus plus the inner electrons. And remember, in our simple model, we have this sort of picture of balls and springs connected to each other, and as the temperature goes up, one simple picture is you can imagine if there's a higher temperature, higher thermal energy, these things start vibrating with a higher amplitude. There's going to be a greater likelihood of collisions as the electrons flow through. And so the temperature, it's the temperature dependence of the mobility in most metals that really is affecting the temperature dependence of the resistance. If the mobility goes down, the resistance is going to go up, and therefore the slope of this thing is going to decrease. Okay? So this is what's called non-ohmic behavior. So here's a question. You have long bulb and 2 batteries, and you get a current of 0.075 amps. long bulb and one battery, and you get a current of 0.05 amps. Is this ohmic, non-ohmic, or can't tell? Remember that each battery has a voltage of 1.5 volts, EMF of 1.5 volts. Okay, it's going to be non-ohmic because it's not scaling linearly. It's not scaling linearly, right? The resistance for one battery is going to be different than the resistance for two. For two, we worked it out to be 40 ohms. For one, it's what, 30? 1.5 divided by 0.005 is 30 ohms. Okay. So the resistance is going up with a larger current and therefore a larger temperature, right? Okay, so non-ohmic behavior. Other things just to keep in mind, that things you may run into in your later careers, other types of non-ohmic objects. Well, a battery for one. Current plotted against voltage for a battery. Well, for an ideal battery, does the voltage depend on the current? No, right? A 9-volt battery is a 9-volt battery whether there's a current flowing across it or not. Now, in non-ideal situations, it actually does change a little bit. We won't talk too much about that, but basically it's like a spike, okay? There's the EMF of the battery, and it doesn't matter what the current is. Semiconductors are kind of interesting. In a semiconductor like silicon or some other sort of material, and it depends on not just the material but also how it's treated, what it's doped with, what types of impurities there are in it. You can have a situation where you apply a potential difference and it behaves like a insulator for a while. There's just no current. And then you reach some sort of threshold, some critical point where then suddenly you start to get a current out of this, okay? And that's a case where what we talked about earlier, the number of available mobile charges actually changes. You reach some sort of critical point where you free up, the electric field becomes large enough to free up mobile charges, and they may be electrons or they may be other things, and we'll talk about that later as well, and can get a current to flow. So this is other examples of non-ohmic behavior. We have maybe just one or two more things to talk about in this chapter. We'll finish those next time, and we'll start on magnetic forces.